I'm glad people have now picked up the knack of joining just at 4 o'clock. And so before this, about 15 minutes before 4, we would have the audience, but now, so we were waiting for people to join, but welcome. And I'm very glad to have Poonam Chandra with us today. And very, very exciting talk. Poonam, of course, as you know, is faculty at NCRA across the road from IUCAA. She, of course, was a PhD student, PhD student at TIFR, working with Alakrai, then went on to be a Jansky Fellow at UVA, Charlottesville, then worked at the Royal Military College in Canada. Amazing, it's in Ontario. And then joined NCRA in 2012 and has been one of the most prominent members of our astronomical fraternity here. Welcome, Poonam, and let's hear about explosions.
All right. Thank you, Shomak, for such a nice introduction. And thank you, Kandu and Shomak, for inviting me to give this talk. I'm really excited to give this talk. And I think one of the reasons is that this topic is really exciting. I'm going to talk about the end products of stellar explosions, these kind of transients. So I'll start by saying that massive stars live very exotic lives. And their deaths are even more exotic. They result in one of the most energetic explosions in our universe. And some of the very, known ones are supernovae and gamma ray bursts, but there are some very new kind of transients also which are emerging. For example, among supernovae, there are variety of supernovae. And the most exotic ones are superluminous supernovae. And currently there are a lot of question marks in the theory of these kind of supernovae, but it is believed that rather than these are not the regular neutrino driven explosions, but they may likely to be the central engine driven explosion. And then there are new kinds of transients which are called fast blue optical transients because of their accelerated evolution. And this is not just the end of the story, because sometimes the remnants of the explosion, like neutron stars, magnetars, and black holes, also take little help from a companion and gives rise to even more exotic kind of explosions. Short gamma ray bursts, electromagnetic counterparts of gravitational wave. Gravitational waves itself, and in some cases, magnetars have been related to found to fast radio bursts. So it is very important to map the massive star and their end products to understand the stellar evolution. And not just that, studying these stellar explosions also provide us that unique opportunity to study the physics at its extreme, which is unavailable otherwise. But it is very difficult task. Unfortunately, there is no mapping between the initial mass to final mass of massive stars, because these massive stars are at a very boundary of the radiative diffusion upper limit. So their mass loss rates are quite high. So they lose a lot of mass during their evolution, and the way the star started with a certain mass, and by the time it is exploding, it is no longer the case. So in that way, mass loss rate is, kind of stopping us from understanding that. It is, of course, impossible to follow through the evolution of a single star all the way from birth to its death, because we don't live long enough, of course. Simulations are a way to do it, but simulations have their own problem. And while we have been making more and more successful simulations of supernova explosion as of now, these are super duper expensive, and it is nearly impossible to catch the diversity of these explosions of these universe. So how do one understand these exotic massive stars? And here, the same thing, the mass loss rate, which we were not happy about, is the one which comes and saves us, because this mass loss rate, this mass loss from the star manifests itself in terms of stellar winds. Now hence these stellar winds are going to carry the information about the star. They carry the footprints of the star, since they were the same mass from the star. At the same time, the ejecta, the stellar ejecta explosion, ejecta, is moving with a very high speed, generally supersonic, and in some exotic cases, relativistic speeds. So there is the ratio of the ejecta speeds to the wind speeds is much higher. So in some way, you can imagine that if you study this ejecta interacting with the surrounding winds, it provides us a fast forwarded way to go back into the history of the progenitor and understand the evolution of these massive stars, because mass loss rates do trace the history of the progenitor star, the way the star lose mass and so on. Now, the beauty is that this interaction, of course, because of the interaction, the shock will be created. The shock will be really hot, and these hot shocks will provide the X-ray emission, thermal X-ray emission. At the same time, in these shocks, electrons will get accelerated to relativistic energies, and in the presence of magnetic field, synchrotron emission happens. And by very property of the synchrotron emission, later and later time, it will peak at lower and lower frequencies. So it at lower radio frequencies, one can trace the interaction in form of synchrotron emission for a much longer time. And radio emission is the most sensitive electromagnetic radiation to understand the density of the medium. So it is the radio emission, especially in fact the rising part of the radio emission, which contains much of the information about the density of the medium and the mass loss history of the progenitor. Of course, the falling part also contains some important information about the electron acceleration, particle acceleration aspects, and so on. So with UGMRT, we are carrying out, we are basically exploiting this fact that the low frequency emission is critical to understand these density environments of these relativistic and non-relativistic explosions. And GMRT serves a very good purpose because one, it is a low frequency telescope, but because of its 30 dishes is spread in 25 kilometer baseline length and each antenna being 45 meters in diameter, it provides the unique combination of high sensitivity, good resolution, and no low confusion noise. So with this, we are following various transients, and as you can see on the bottom right, bottom of the plot, in most of the cases, we are able to look at this optically thick radio rising part for a much longer time. So in this talk, I am going to give you some examples of non-relativistic and relativistic explosions and their studies in radio and X-ray bands, and how they have enhanced our overall understanding of stellar evolution of massive stars and their explosion. So the first one I will be talking about is the supernova, which is called J1204 in a short form. Now, supernovae are those end stages of the star where a star has run out of its nuclear fuel. There are no more nuclear fusion happening, so there is no more radiation pressure to keep the star stable, and star will implode under its own gravity. And at some point, this implosion will turn into an explosion. The time of the explosion, what was the condition of the progenitor star, that will determine the kind of supernova. In this particular case, the spectroscopy told us that when the supernova exploded, at that time, it had lost all of its hydrogen envelope to mass loss. Now, that's a different story, how it lost its mass, whole of the hydrogen envelope, what exactly happened. But we do know that it had lost all that mass. We studied this supernova in very detail, all frequencies of the GMRT for around 3 years. We also observed with the VLA for almost around the year, and there were observations with Chandra and XRT. And we were able to study the evolution of light curve and spectra at multiple frequencies owing to the low frequency data, which actually contain much more information than we were anticipating. So for example, if you look here on the left side of the plot, I'm showing you the low frequency spectral index. And for around 70 days, the spectral index is 1.4. Now the thing is, if the radio emission is absorbed by synchrotron self-absorption, it should have been around 2.5. If it was a free absorbed, it should have been even steeper. So this does not satisfy the known models, the standard circumstellar interaction models. Now, if you look at the right side of this plot, this is the light curve, and one can fit this light curve very nicely with synchrotron self-absorption model, but this is the light curve at a single frequency. It does not contain information. The frequency parameter comes under normalization. So if you look at if you try to derive the physical parameters from this light curve, you get the very, very hard particle energy index. It's of the order of around 1.5. You get the size of only few times 10 to the power 15 centimeter, which is not possible for two reasons. One, from the optical helium line, it was seen that the size of the photosphere was 2 times 10 to the power 16. At least 3 times at least 2 times larger than what was seen in the radio band. And this is not possible because radio is coming from the forward shock. Radio represents the fastest ejecta. The energy in the radio bands represents the kinetic energy of the fastest ejecta. Now here the radio observations are giving the size which is smaller than the optical, and it is not possible. Second, if you look at the VLA data, the particle energy index is of the order of 3 and not 1.5. So something is wrong. And in this case, my screen has frozen. I don't know how to go to, oh yes. So in this particular case, we modeled this circumstellar interaction in terms of inhomogeneous radio emitting region. So the idea was this, and let me just tell you that it had been talked about little bit sparsely in the literature, but since there was no detailed low frequency data, it was never taken up seriously by the community. But the thing is, when we take the synchrotron emission, we assume that the forward shock has a uniform distribution of electrons and magnetic field. But magnetic fields are created due to the Rayleigh Taylor instabilities around the contact region between the medium and the supernova ejecta. So there is no reason for this to be very homogeneous. So the way we explained it, little bit analogy you can take from the AGNs, that there are the synchrotron self-absorption components are there, but there is inhomogeneity in the magnetic field. So each component of the magnetic field will correspond to a different optical depth, and it's the superpositions of the different optical depth which is giving rise to the optically thick spectra, and this superposition is broadening the spectra or in some way making the spectral index slightly flatter. And we developed that formalism based on this, and we parameterize this magnetic field in terms of a covering factor of magnetic field. And then we modeled our data. We predicted the peak frequency and flux variation, and then when we check it in our data, it certainly matches with the inhomogeneous model. So this is, in some way, this is the first representation of that the shocks which are emitting the radio emission are not really inhomogeneous in some supernovae, and this is that case where we have shown that. Now the second example which I'm going to give you, because this supernova is really very close to my heart and I really like this science. No, I'm sorry, I wanted to, before getting that, I wanted to just say one more thing about this particular supernova. And the thing is that in this supernova there was another surprise. The thing is, here you can see the radio spectra at various epochs, and these epochs are between day 47 to 900. Now, as per synchrotron model, the peak should go to lower and lower flux, speed should go to lower and lower frequencies, all good. But if you see the red and the blue spectra, you will see that it should, the first one should have been around the orange line. There is hardly any evolution between the two spectra, and if you look at the time evolution index, it's very close to the zero, as if in those 2 months the shock completely stalled. It did not move, and then it came out of that and it started following the standard kind of evolution. We initially thought that maybe there was a high density shell, this green curve on the right hand side, and this green shell on the right hand side, and shock is moving through that. And it kind of made a very nice physical explanation, because since this supernova was a supernova which did not have hydrogen, which had lost its hydrogen envelope. So maybe we are seeing that hydrogen envelope and interaction of the ejecta with that hydrogen envelope. But our Indian colleagues, Kuntal Mishra and her group, they were doing some optical observations, and then we asked them, and they said that they had not seen any hydrogen at this epoch. So it means it was not the lost hydrogen envelope. And anyway, it's very difficult to explain the hydrogen envelope so close to the explosion. So this is I think we can explain this in the form that just sometime before the explosion, say around 2 years or so, there was an episode of very enhanced mass loss rate which created this dense shell. And if we do a very simple back of the envelope calculation, it must have corresponded to sorry, this we saw around day 50. So around some few hundred years before the explosion, and this corresponds to carbon neon burning phase. So at that time, we are seeing this enhanced episode of the mass loss rate. So this is so basically the mass loss rate from the start does not go at a very uniform pace as has been considered so far in the literature. And here we have shown this case. Now the second supernova is a supernova which showed metamorphosis. And before saying this complicated word, let me just say that the traditional classification of supernova is very confusing. If I go into the traditional classification, I would be talking right now about type 1b, type 1c, type 2b, type 1n, type 2n, type 2p, and type 2l, and you will lose the interest in this talk right away. So the way I'm trying to determine is show you is that at the time of progenitor, whether it was having the hydrogen, whether it was having no hydrogen, no helium, whether it was a thermonuclear explosion of a supernova, or whether it was a gravitational collapse. And this particular supernova, 2001 EM, is an extremely interesting example because when it exploded as a supernova which had lost its hydrogen as well as helium envelope. How did it lose? We don't know, but it had lost at that time. Now, at that time, it was a very hot topic to search for off-axis GRBs from these kind of stripped envelope supernova, because some GRBs had shown this connection between supernova and gamma ray bursts. The first one was 1998 BW supernova with 980425 GRB, and then in 2003 this was 0303 to 29, for which there was a very long campaign. So inspired by that, there were many stripped envelope supernovae which were observed late time in radio and X-ray bands to look for this off-axis GRB. And this supernova, 3 years after the explosion, it showed a bright radio and X-ray emission. And initially, as one can imagine, this was modeled with an off-axis GRB, and there were publications on that. But when the VLBI observations happened, the velocity estimates were made. The velocities were less than 6,000 kilometers per second. There was no way it could have been a GRB. And also the optical spectra was showing the hydrogen. This was also inconsistent with the GRB. And later, Roger Shivali and Nikolai Chugai modeled it as a supernova ejecta interacting with the hydrogen, the lost hydrogen envelope of this progenitor star. And that was the explanation which fit the most. In this case, we collected 20 years of data. Our last observation was in June 2020. We had data with the Gmrt, we had the data with the VLA, Chandra, XMM, and SWIFT, and we carried out probably the most detailed circumstellar modeling after 1993 J. And here, this supernova, the modeling of early data is very interesting. If you see the early radio light curve on the right side, the top 2 panels, it does not show any matching with the standard model. If you see the X-ray, after around day 1700, it starts to fall very, very fast, T to the power -3. So we took the both inputs and we say that the first 2 data here are consistent with very high optical depth because of this red part, the dense shell that the supernova. See, remember the supernova was first observed after the very initial non-detection, first observed in the radio and X-ray band around 800 days. And at that time, the supernova was already in this dense shell. And around day 1700, the sharp decay of X-ray is representing that by around this time, the phase 2, later the phase 2, the supernova had come out of this dense shell. And when we modeled this dense shell, we came out with the result that around 2.5 solar masses of hydrogen shell must have been ejected around 1000 years ago before the explosion. And this is what we are seeing the interaction with. Now, generally, if you see the cases of supernovae, the stripped envelope supernovae come from Wolf-Rayet stars, which do not have hydrogen and helium envelope, and they have a radius of around 10 to 12 parsecs, and the supernova shock generally takes a few hundred years to reach those hydrogen shell. But here in 2001 EM, and let me just tell you, this is not the only example, there are some more examples. The shock had hit the shell in just a few hundred days, which means the outer envelope was lost just 1000 years ago. This is a very large mass to be lost, like 2.5 solar masses, just 1000 years ago before the explosion. And luminous blue variables could be one of the cases, but they generally tend to show a lot of hydrogen from the very beginning, and they're not expected to lose mass this close to at the time of supernova explosion. So we didn't understand what kind of progenitor it was, but there was a very interesting answer which lie in the late time data. Now, if you look at the late time data, if the X-ray observations are showing that it is moving in a, now after the dense shell, it is moving in a regular rare medium, we expect the optically thin spectra, which it was showing until it started to rise around 6 gigahertz. And now you see it's going to the optically thin, and these are our June 2020 GMRT and VLA data. And then it starts to rise and come back again. This is probably the most interesting feature we have seen in this supernova. And this is a spectra on day 6000, or around 15 years after the supernova explosion. And let me tell you that this is the second only supernova to have shown this. The other supernova we showed this was supernova 1986J, which in the middle plot I have plotted in the blue line. And on the left side, it shows multiple epochs. It is showing exactly the same kind of feature. It is showing that it is optically thin, then suddenly it becomes optically thick, and then it goes down again. And on the rightmost, you can see the VLBI observations at multiple epochs. You see there is a component which is giving rise to the radio emission, and after, if you go down, you see the on the right, bottom right, the second component starts to appear. And then if you go to the second column, the second component starts to become more prominent, and by the end of the observation, the first component is gone, and it's only the second component which is there. This has not been seen in any other supernova. This supernova 2001 EM is too far away for us to do VLBI. It's 80 megaparsecs, but this one 86J was very close, and this we could see this shift of the radio emitting blob, and multiple explanations were given for this supernova. But finally, the most acceptable explanation was that we were probably seeing the common envelope scenario. What that means is there were two massive stars in a close binary. The bigger star exploded as supernova, created a neutron star. Now the other star, which will explode as my supernova 2001 EM, this neutron star spiraled into the supernova, accelerated the mass loss, made it eject the hydrogen and helium shells, created a very asymmetric circumstellar medium with much more a bulge around equatorial region. And initially we were not seeing that equatorial region, that is this optically thick part, because the shock was optically thick. And but once the shock became enough optically thin, we start to see the dominance of this slow moving, highly dense blob of circumstellar medium. And this is, of course, this is a circumstantial evidence, but this is something which has been talked a lot in literature, starting from supernova 1998 S time, and it has, but this is the late time spectra. We are actually seeing a circumstantial but very, very convincing evidence of this kind of progenitor system, which is not an LBV, but it is a common envelope scenario. And this has very important implications for example, binary mergers in advanced LIGO, because these kind of systems exist and one can see, and because they will eventually make the two close by neutron star systems. Now, having talked about non-relativistic explosions for a while, let me come to the relativistic explosions, gamma ray bursts. These are, I would say, the more exotic counterparts of supernovae. In this case, the explosion is super relativistic. The ejecta moves out with speeds as much as 99% of the speed of light. And they were discovered in late 1960s and reported in early 70s. And for 30 years, we didn't know what they are. But eventually, in late 90s and early 2000s, one started to understand that they are probably the most exotic aspects of very massive star explosions. And eventually, the gamma ray bursts did show some connection with supernovae. And it turned out that what we were thinking in terms of massive star association was correct. And later it turned out that there were two populations of gamma ray bursts. The other one was the short gamma ray burst, which was likely the merger of two compact stellar remnants, and which at least one was neutron star. And this has been directly proven just 3 years ago after the discovery of gravitational wave from one such system. So this is about gamma ray bursts, and with such high relativistic ejecta, they show synchrotron afterglow emission, which is all the way from X-ray, optical, infrared, radio. But again, this virtue of synchrotron, it is much long-lasting emission in the radio band, and one can observe the transients, these explosive transients in radio band for much longer time. And in GRBs, they have very important implications. One, the nature of surrounding medium reflects the nature of the progenitor. For example, the surrounding medium for massive star GRBs versus the compact object merger GRBs are entirely different. The second thing is that the afterglow brightness in the synchrotron mainly depend upon the two key parameters, the kinetic energy and the circumburst density. Now, if you go into X-ray and optical afterglows, they are degenerate parameters, very difficult to differentiate the two. But it is the only way in radio band by the optically thick rising part that one can constrain the density separately and energetics and break this degeneracy. So it is very important to get the true calorimetry, which happens only by the radio band. Now in GRBs also, there is a different class of GRB. In the GRBs from the massive stars also, there is a different class of GRB, which is 10,000 times less luminous than the regular GRBs. And as you can see on the right hand side curve, the top one is a low luminosity GRB. They have a very smooth light curve as opposed to the long GRBs. They rarely show jet breaks, and so it has, the relation between the long gamma ray bursts and low luminosity GRBs is a long-standing puzzle, and it's not really very clear what these are. As you can imagine, most of the theories believe that it's simply off-axis GRB, but the fundamental properties are not of that of a off-axis GRBs. Very few people believe that. But the good thing is that some of these or most of these low luminosity GRBs have shown association with the supernova, and the supernova is of the same type as one sees in the long GRBs, regular long GRBs, and that tells us that there is a similar kind of explosion mechanism which is taking place in these low luminosity GRBs. So there are, as I said, there are many theories: jet off axis, supernova breakout. But one of the more accepted theory is that these GRBs are surrounded by this dense envelope. So when they are surrounded by dense envelope, the jet which was to come out, the jet interacts with this high density envelope and gives away its energy or loses its energy to this envelope, and this envelope comes out as a slightly collimated, widely collimated shock breakout, or in some way you can think of a cocoon breakout. and the jet dies in between before even coming out, and this is the shock breakout we are seeing, and that's why we are not seeing the jet break, and we are seeing the less energy and so on. So these are some of the models of the low luminosity GRBs, and but you can see the density is again a very important part here. So we got a chance when the GRB 171205 came into picture. This was the low luminosity GRB with the supernova associated. It was low luminosity, but not really as low luminosity as the other regular low luminosity, but still, because though they have a very long duration, they have a very soft spectra, but this was somewhere in between. There was a first of this GRB, that was for the first time the early epoch cocoon emission was seen in optical spectroscopy, and this paper was published by Izzo et al. In Nature in 2018, where they said that in the supernova spectra they saw this broad line, featureless continua, where this shock was moving with the velocities of 1/3 of the speed of light, and this was the cocoon emission. And so this is the first where it was seen directly, and we carried out the Gmrt studies with 250 and 1400 megahertz band. And as you can see in the leftmost, the blue one is the GRB 171205, which has been compared with the GRB upper limits in black and detection in orange, and it is much lower than the other radio detected GRBs. This is the first GRB to have been detected at a frequency as low as 250 to 500 megahertz band. So this is the lowest frequency detection. We have followed it up for 3 years, and this work was mainly done by Varun Neti, who did a project with me. And the thing is that if you follow it up for 1000 days, one can study the evolution. And if you see the multiple peaks, one can not just constrain the density at epoch, one can even constrain the evolution of the density with time. And that was the unique opportunity we had this with GRB. And if I'm showing you here, you see on the right, this is the GRB Gmrt light curves, and they are moving at later and later time to lower and lower frequency, and the flux is declining. Of course, these are scaled, but if, to show it clearer, but flux is declining. It clearly showed that the GRB was exploding in the wind medium. You can see on the right is the Chandra data. These are the blue ones are the archival Chandra data which we analyzed, and it is very clear that up to 70 days there is absolutely no jet break in the GRB. On the left side, the plots, these are the SEDs from 0.4 gigahertz to X-ray bands from day 4 to 900 days. And this is the first time we have been able to get so much SED for such a long time. And you can see even the 900-day SED has the turnover, which allows us to constrain the density in which the GRB was moving even at that late time. So this allowed us to really carry out a very detailed modeling of the gamma ray burst, and it gave us an opportunity to check for the shock breakout versus the jet model, and we fit both the models. The model could not differentiate between the two, but we did try to fit the general density medium so that if the mass loss was variable as expected in the pure shock breakout model, whether we are seeing that or not. But if we take the optical spectroscopy, and in the optical spectroscopy, Izzo et al. Had seen that this cocoon was moving with 100,000 kilometers per second. And the reason that this was the first time cocoon was seen is because if the jet is on axis, the jet is so bright that you do not see the cocoon. If the jet is off axis, you get to know about GRB only by seeing once the supernova starts to come up. But by the time you see the signatures of the supernova, the cocoon is already gone. So, but here, these people figured out that the jet was slightly off axis. The jet had high energy of the order of 10 to the power 52, but it was showing low because it was off axis. But initial data had this evidence of cocoon. And our model very clearly showed that early time emission could very nicely be fit with the cocoon shock breakout model from this cocoon. And the late time, there was a flatness in the light curves, and they showed that the contribution of the jet had also appeared. And later time, we were seeing the contribution more and more increased uh, contribution from the jet. This is a GRB which is still going strong, and this is GRB which we are still continuing to observe with the Gmrt. So we will actually know soon in a couple of years whether what we have predicted is correct or not. Now, when we are talking about the GRBs, it is not possible to not talk about the first binary neutron star merger, even though I think many of you have heard me talk about this particular thing, but I would just like to say something very quickly. This was very special and I think close to everybody's heart, because this was the first binary neutron star merger with gravitational waves and electromagnetic counterpart, and the emission in all full spectra of electromagnetic spectrum was seen from all the way from gamma rays to radio. The Gmrt observation was the lowest frequency observation in this case. There was a delayed non-thermal emission in X-ray and radio band, and a very long and very detailed campaign was carried out. But it was the radio observations, radio modeling at early time, which very strongly suggested that the early photons we were seeing were not from the jet, but from the cocoon. And the model was that this jet, again, the same analogy with GRB 171205, the jet was giving rise to its energy, losing its energy to this polar ejecta, and that ejecta was giving rise to the early emission. But later on, the modeling with multiple telescope across the world in radio band, including GMRT and VLBI, very clearly showed that eventually the cocoon had stopped dominating and jet had successfully come out of the cocoon. It did not lose all of its energy. Exactly the same way as in the previous case also, the jet did not lose all of its energy as it was claimed in the car shock breakout model. The jet did come out. It only gave some of its energy. And even in this case, it gave some of its energy. And so it means some neutron star mergers do power short gamma ray bursts. And this is a very important conclusion for this particular case. Now, the story doesn't end here. If there's a kilonova emission, the kilonova is subrelativistic. It's expected to interact with the medium, and it is expected to peak at less than 1 gigahertz frequencies. There have been campaigns going on with X-ray and high frequency VLA emission. It has not been seen. On the right, what you see are different models, and on the yellow to red lines are the lines for different densities, and that depends upon what kind of emission, radio emission one will see. Unfortunately, in this case, when we observed it with the GMRT first, it was already in the optically thin regime. It means we could not constrain the density, even though our measurements were the lowest frequency measurements. Had we had this turnover, synchrotron turnover, this density ambiguity would have gone. Right now, this limits is from the order of 10 to the power minus 4 to 10 to the power minus 1 per centimeter cube. If we had more proper density measurements, we would have been able to predict it much better. But since this is a unique object, we have written a proposal to carry out the observations at late time, and we are trying to look for this ejecta, and this will tell us many more things. And now, in the last 10 minutes of my talk, I'm going to deviate from these purely non-relativistic and purely relativistic explosions, and I'm going to talk about something exciting, which is, as I said, superluminous supernovae. These have been seen in various wide field optical surveys, Assassin, ZTF, Palomar Sky Survey, and so on. This is this rare class of supernovae which have luminosities 10 to 100 times larger than ordinary supernovae. There are multiple theories for this supernovae. If they are explosions, regular explosions, you need around 50 solar masses of nickel to do the radioactive decay to get so much of optical luminosity, which is very difficult to explain. So many people believe that these are probably not the regular neutrino-driven explosions where 99% of the energy is carried by neutrino and only 1% comes in light. These may be a central engine-driven explosions where at the center there may be either a black hole or a magnetar. And it's the spin down energy of the magnetar which is powering the central engine and giving rise to so much of light in the optical. There are also theories that the density is very, very high, surrounding density, and because of that, the ejecta is giving almost all of its kinetic energy to the radiation with this interaction of high density medium, and that's why one is seeing so much of optical emission. There are also theories that the very massive star, in this very massive star, even before reaching to the silicon burning stage, the tail end of the Maxwellian photons, which have temperatures more than billion Kelvin, these photons will create electron-positron pair and then reduce the radiation pressure, and hence the star will start to collapse at the core very soon, and then that will create this pair instability supernova, and the whole star will just disrupt and give rise to so much of optical luminosity. So there are multiple theories. We don't know which one is correct. But recently, magnetar is one of the more favored model. And recently there has been a connection to a very low luminosity FRB, fast radio bursts with galactic soft gamma repeater SGR 1935 plus 2154. So with this, it is very interesting. And even in the other case where there is the only, the first repeating FRB 121102, there has been a connection that the persistent source of a FRB is likely to be a magnetar inside a superluminous supernova. So with this, it is very interesting to understand superluminous supernovae. So far, there are only 3 radio bright superluminous supernovae. The PTF 10 HGA, which was discovered for the first time 7.5 years after the explosion. 2017 ENS, which was reported just the last month, 3.6 years after the explosion, and supernova 2020 TCW, which was discovered in radio band just 3-4 months after the explosion. So this is just, it's like literally everywhere, and we don't know what we are looking for. So this PTF 10 HGI is the first superluminous supernova to have been detected with radio emission, and VLA first saw it by the group of Tamanna Tikari, and they saw optically thin emission. Once they were detected, we carried out, and in fact, this work was carried out by 3 NCRA students, and we carried out Gmrt observations all the way from 600 megahertz, and we also took some new VLA observations, and we carried out a detailed analysis of this data. One is that we saw a very flat spectra between 1 to 15 gigahertz, and this kind of flat spectra does not match with the regular synchrotron emission, but pulsar wind nebulae have shown this kind of flat spectra. And with the turnover, we also could constrain the size, which means the speed, and also the magnetic field. Now the speeds were much smaller. It was less than 3,000 kilometers per second. So they were more in tune with pulsar wind nebula. So overall, it looks like that it was the pulsar wind nebula, magnetar wind nebula is the origin of the radio emission. And the total energy is around 10 to the power 47 ergs, or the injection rate of the magnetar is of the order of 10 to the power 38 ergs per second. So this we can show from the energetics argument that this is likely to be powered by the rotational energy of the magnetar or spin down of the magnetar. And so because of this turnover at radio frequencies and this detailed spectral analysis, we could come up to these conclusions, and we did not stop there. We actually took the archival data for FRB 121102 because this was the first repeating FRB where the persistent source in the VLBI observations were seen, and thought that it could be a magnetar at the core of a superluminous supernova. So we took some of the archival data, we used the published data, and we again could, because of this wideband spectra, we could constrain the emission models. What we noticed is the injection rate is more than order of magnitude higher than FRB 121102. So it means if one thinks that we have seen SGR 1935 to show a very weak FRB, FRB 1211O2 has shown a repeating FRB of reasonable strength, and if PTF10 HGI has to power FRB, it is going to be much weaker than FRB 1211O2, but it is going to be brighter than our galactic SGR. So it is very speculative, but you can see one can start to build a picture, and maybe there is a continuum of the FRB energies, and what we are seeing at high dispersion measures is the one which are the far away ones, which are the bright FRBs. But this kind of takes us in that direction, and this is very exciting. And last but not least, I will be talking just for a few minutes about this fast blue optical transients. And this this is probably the newest class of transients which have been connected with stellar explosions. They have a very fast rise time, less than 3 days, very fast fall time, decline time, less than 12 days, very blue, which means the temperature is of the order of 15-20,000 Kelvin. The optical luminosities are very high. It is extremely difficult to explain them in the light of radioactive decay of nickel 56 kind of models. There are multiples of models. There is in fact no dearth of model. The compact object like formation of black hole, magnetar, a tidal disruption event, merger of two white dwarfs, jet-driven collision, and failed supernovae and whatnot. Every model has been given. But what FBOTs have shown that they are much higher than supernovae, slightly lower than GRBs, but they have a lot of medium around. So if one has to explain this new class of transients, one has to accommodate this extra, this dense medium. And in fact, two of the FBOTs have shown hydrogen in their spectra. So medium has enough hydrogen, which is not the case with gamma ray bursts, which do not show any hydrogen in their spectra. There are only 3 FBOTs which have been detected in radio bands. All 3 of we have followed it with Gmrt. For 8012 18 cow, which is called the cow, this we have carried out a very detailed campaign. In fact, this got accepted in ABJ letters just yesterday, and this comes in the Astro PH today. And we have also carried out the campaign of others, and we are seeing a variety of differences. For example, in terms of speed, we see the mildly relativistic to subrelativistic to non-relativistic speeds. We are seeing hydrogen in 2 of the 3, especially cow and CSS 161010. In fact, CSS 161010 is one of the nearest FBOT, the second most. We followed it with Gmrt for almost 1.5 years. And while the early VLA data showed around 60% of the speed of light of the outflow, the later time, the Gmrt observation around 1 year later also showed around 45% of the speed of light. So it means it had not slowed down despite having so much of hydrogen around it. And this is a mystery, that what could be such a powerful central engine that it allowed us to flow, go with such a high speed in such a dense medium. It certainly cannot be a regular supernova. There has to be a central engine, and we are certainly talking about this rare class of hydrogen rich transients which have a higher speed. Now the second, this is the figure I was showing, so we have to explain that. The second one is the 2018 cow, and this is some papers have come out of it from millimeter observations, X-ray observations. Some paper have talked about maybe a tidal disruption event with an intermediate mass black hole. We have carried out Gmrt observation, and this is the paper only with Gmrt data, and we have shown 600 days of data, and we have shown few things. And for example, the shock is highly inhomogeneous. The speed, the early time speed from the millimeter data was only 10% of the speed of light, but we are now seeing it's going around 20% of the speed of light. The mass loss rate at early time was 100 times larger than now, which means there was a very enhanced density medium in the early time, and now late time Gmrt observations are showing that it has come out of that huge dense medium, and yet it is going strong. It is very bright in optical, and Well, we all are wondering what exactly is this, but just a couple of days back, there was a press release and a paper in the archive. And let me just tell you, the people have this habit of naming pots on the name of animals. For example, AT cow has been named as cow. The ZTF, the other one has been named as koala, and this one, the latest one, has been named as camel. So, so basically, the cow, koala, and camel, these FBOTs. There's a paper. This is the latest FBOT to have been detected, and Brian Musker has explained it in the following form. They are saying that instead of collapsing into a neutron star, in a massive star, the core directly collapsed into the black hole. When it collapsed into the black hole, most of the mass fell into the black hole and there was no supernova. But as this black hole ate the outer layers of the star, it begins to spin very rapidly, and then it produced a very powerful jet from its poles or rotational axis. And this is what we are seeing now. We are seeing this, and because of these black holes and very powerful jets, we are seeing that even though there is a high density medium around it, as it would be, one would expect in a normal massive star losing mass, but these jets are able to navigate through this medium. So this is the latest theory which is coming for FBOT, and we don't know how much it is true, but we are trying to follow these and trying to understand that. And at the last, I would like to say that there are, very maybe probably small differences lead to very different kind of explosions, and there is also possibility that in some cases there is no photons coming out. No, it's just that it is collapsing into a black hole, but it doesn't mean that they are not explosions just because we are not seeing with our telescopes. But these are explosions, but these cannot be seen in photons, and that's gravitational waves are the another messenger which will be seeing these kind of explosions. And we have already seen that binary black hole mergers have been seen from via gravitational waves with advanced LIGO. In fact, in the first one, we have seen the 3 solar masses and highlight in like just a few seconds, and this is like unprecedented. So a gravitational wave, and with advanced LIGO, it is uh, extending its reach much higher, further away in the sky. It is going to probe these new kinds of transients and will tell us about what are these failed supernova GRB kind of transients. And I think LIGO India, IUCAA is pretty heavily involved. So it is a very good time to pursue this kind of transient physics with LIGO. And I would like to end my talk with these cute animations where on the right hand side, I'm showing the supernova discovered from 1900 to now, and you can see the number of rates are increasing. And on the left, I'm showing the gamma ray burst discovered with SWIFT. So there are many dedicated telescopes to look for these exotic transient phenomena. There are many robotic surveys, ZTF, Palomar, we have Assassin, we have so many surveys carrying out. There are many more telescopes. LSST is coming online very soon. So it is time that we gear up to follow and understand these stellar explosion. Of course, we are in India, we are very well placed. We have a lot of telescopes in optical. We have DOT, we have Himalayan telescope, we have Growth India, we have some more telescope, we have AstroSat, we have GMRT, and we are going to be part of TMT. In LIGO India will come very soon, and India is a major part of SK. So these are very exciting times in this particular field. And I think with that, I will end my talk and take any questions. Thank you.
Thanks very much, Poonam. Thank you. This is you made a very strong case for transient astronomy, and particularly that was a very striking last slide. Any questions? Please raise your hand. Following our normal convention, Zoom has hidden the raise hand option in the reactions button below. So please raise your hand. Yes, Pranjit to begin with. Pranjit, go on.
Okay. Poonam, nice talk. So since you made this connection with gravitational waves, my question is about direct detection of supernova with gravitational waves. So the observations you are conducting for different supernova, so the model is that the shock front is sort of, it is very symmetric, right? Spherically symmetric. So is it possible to study, like, if there is any asymmetry involved in this emission, which can then tell us something about whether there will be a direct gravitational wave detectable from supernova?
Yeah, actually, this is a very good question, and there are multiple answers to this. One of the answer is from the say simulation point of view. There has not been, people have not been able to explode supernova if they're perfectly symmetric. So there are some kind of asymmetries are needed. Second thing is that there are a lot of polarimetric observations are happening. And in fact, recently I requested, Kuntal had a program in India and then she terminated that program after her student left, but I requested her. There are enough supernovae which are showing high polarization factor, and these supernovae are showing highly asymmetric explosion or ejecta and CSM. So there is a asymmetry. When we are carrying out radio and X-ray observations from the column densities and the way circumstellar medium is manifesting itself, we can circumstantially but very confidently tell that there are huge asymmetries. And once there are asymmetry, it is just a matter of sensitivity. If you had an ideal gravitational wave detector which could reach anywhere in the sky, you would be able to detect supernovae from gravitational waves from supernovae. But I think right now the limits are very close. If I'm not wrong, I had read somewhere that a reasonable supernova with the reasonable asymmetry, one can detect, say, within 60 parsecs, which is a very, very difficult to do that. But hopefully in the future with more advanced LIGO, it should be possible. Shomak, you are muted, so I can't hear you.
Next is Dipankar in line. Yeah.
Hi, Poonam. Very nice talk.
Thank you.
I may have missed something, but you did talk about the fast radio burst, connection between fast radio burst and superluminous supernovae. Is there a direct observational evidence for this, or is this still a conjecture?
There is if you want to say direct evidence, so the SGR 1935 plus 2154 in our galaxy had revealed very faint radio bursts, and that if you put it at higher redshift, you will not see them. But these look exactly like a lower energy version of the regular fast radio bursts, which we detect with the CHIME and SCAP and all these Parkes telescopes. So that is in some, and this came from the soft
and fast radio burst. But
this came from soft gamma ray repeater, which are considered to be active magnetars, right? So that's the connection.
No, but direct evidence of superluminous supernovae containing a magnetar is not seen yet, right?
No, that is not there. It's just that there are the superluminous supernova luminosities are so high. As I said, the nickel 56 is not able to explain, and then one needs some kind of central engine, and magnetars are one of the very favorable engines. So people are just trying to explore this. There is absolutely no direct evidence.
Right. Okay, understood. Yeah, thanks.
Shukanto is next. Shukanto, go ahead.
Hi, can you hear me?
Yes, Shukanto.
Nice talk, Poonam. So, yeah, I was curious about, you know, the late time radio emission from 1708-17 or the lag thereof. So I think you're using it to put some constraints on like the electron density of the circumburst environment. And it has been, what, some years already. Can it, I mean, there are confounding factors, right? It's not just about the density. It also ties in with the specifics of the burst itself, right? So if you don't land up seeing anything even in the next year or two, how conclusive can you be about about where this burst actually occurred in NGC 1993?
Yeah, so let me start with saying that it certainly is not just a function of density. It also depends how much energy went into this polar ejecta, right? And that kinetic energy is quite critical. It's just that if we had the density information, we didn't need to work with E into N. We could just work with E just separately and just constrain the energetics. Now we cannot constrain the energetics separately. But what the motivation to do it is that there have been 2 papers where they are seeing, Chandra is seeing it in X-rays up to 5 sigma detection. So there is a late time X-ray enhancement. And if I can just quickly maybe go back to this plot, I can maybe, since I was talking so fast, if this, you can see there is a slight axis of X-ray. This is X-ray light curve. And since there was an X-ray axis, and X-ray is also supposed to come from this ejecta interacting with the medium and creating the shocks which gets heated, it was natural to search for this emission in the radio band, and VLA has been doing it 2 to 4 gigahertz. But they are not that energetic. They're supposed to peak at sub-gigahertz frequency. So we have, from this year itself, we have started to do that campaign. But the thing is that there are various models. Some models say that this will come like 5 years after the regular jet. Some models it will come 10 years down the line. So I think our idea is that this is such a unique event that maybe we should do once every year for 5-6 hours and see if we are detecting anything or not. So that is the goal right now, because we are really, trying to see something which very little is known.
Yeah, I'm happy to hear that the campaign is on. I
Yes.
also agree that this is important to encash on this opportunity.
Yes.
Thanks.
Just 2 days back, in fact, yesterday Archive had a paper by Arvind Balasubramaniam and Alessandra Corsi on 3 gigahertz upper limits on the radio band at late times. So campaign is pretty much on.
Excellent.
Yeah.
Thanks.
Yeah.
Thanks very much. Kandu next.
Hi, Poonam. Interesting, very interesting stuff, various things. One thing I was very intrigued by is this explanation of very flat self-absorbed spectra with some inhomogeneous model. So this was inhomogeneity in the magnetic field, inhomogeneity in the, what was the inhomogeneity in?
Yeah, so the way we have parameterized it, we have introduced a factor which is, if it is 0, it shows inhomogeneity of the magnetic field. If it is 1, it shows the inhomogeneity in both relativistic electrons and magnetic field. But because of the complexity of the model, where you can include the inhomogeneities of the both, we have sticked ourselves only to magnetic field inhomogeneity. But yes, I should say that it is not really, and we thought that is more likely, because since magnetic fields are entangling and enhancing at this shock contact region, so it's more likely to have this kind of inhomogeneity. But you are correct in saying that there could be inhomogeneities in the relativistic electron distribution also. So our formulas does account for that. It just is practically very difficult to implement it. So we have not yet fit any of the data with that model yet.
So do you get some scale for this inhomogeneity, or is it?
So we are able to put an upper limit, and we are also able to predict that the inhomogeneities will decrease with time. So we are hoping that eventually in a year or 2, we will see in band 3, we will see this evidence. We are not able to put a precise constraint. If we had a VLBI, we could constrain the brightness temperature. We could from the size directly, and we could precisely tell about inhomogeneities. If we had inverse Compton, for example, in X-rays, we could constrain the microscopic parameters, how much energy is going to relativistic electron, then we could have parameterized it more correctly. But here, none of X-rays are not detected, so it's too far away for VLBI. So that's where we are, our hands are tied actually.
Thanks. I would be happy to get a reference to your paper.
Sure, I will send you. I'll send you an email.
Thanks.
Okay.
Thanks very much. Anybody else with questions? I don't see any questions in the YouTube part of it as well. Okay, if there aren't any, then let's applaud Poonam, and thank you very much for a very, very interesting talk. And,
Thank you.